Welcome to Algebra 2. Today we've got our first section of Chapter 4b, the Fundamental Theorem of Algebra. Now, it seems like it's taken a while to get to the Fundamental Theorem of Algebra. You've been doing algebra for 3 years now, but we finally made it. The Fundamental Theorem of Algebra was devised by a man named Carl Friedrich Gauss, and basically found a pattern that if we have a polynomial function that has a certain degree, remember that's the highest power that we see on a variable in our function, then when we try to find the zeros or set that function equal to 0, it will have exactly n solutions. It will have the number of solutions that matches that degree. And we've already seen this come up, right? When we had studied quadratics in Chapter 3, we found that we got 2 solutions every single time that we went through. And they may have been real, they may have been imaginary, but 2 solutions, those quadratics are second degree polynomials. So they had degree 2. All right, so these solutions can be real or imaginary, and we may also find that we get irrational and imaginary solutions. Those always come in conjugate pairs. If we think about quadratic formula, plus or minus the square root, that's where we would get imaginary, that's where we would get irrational solutions. They're always trailing that plus or minus. So those conjugate pairs, if we were to sketch out a couple instances, if we were to do quadratic formula and get 3 plus root 2, 3 minus root 2 would also be paired up with that because of the plus or minus in front of the square root. If we were to go through quadratic formula and get, say, 3 plus I root 7, then 3 minus I root 7 would also be included because the plus or minus is in front of that square root. Likewise, negative 2 plus root 17 means its conjugate, negative 2 minus root 17, is also a solution. They come in those pairs. And it's always the sign that's on that square root term or wherever we found our square root, because that's where plus or minus came in quadratic formula. All right, so our first task is just to very gently work our way into the fundamental theorem. We're going to look at some polynomials here. You can see some of them are written in function notation, others as part of an equation set equal to 0. And we're just going to try and find how many solutions, if it's an equation, or zeros, if it's written as a polynomial, this function has. So for letter A, we've got 5y to the third minus 3y squared plus 8y equals 0. All I'm concerned with is the highest power I see on my variable. That is a degree 3, third degree polynomial. It has 3 solutions, or 3 zeros. For letter B, f of z equals negative 7z to the fourth plus z to the second minus 25. All I'm concerned with is that degree, the highest power I see on my input variable. In this case, it's a 4, indicating 4 solutions for that polynomial. Or zeros for that polynomial. I should use the vocabulary correctly. And lastly, letter C, the function h of x, 5x to the fourth plus 7x to the 8th minus x to the 12th. Want to be on the lookout here. If we're in standard form, the highest power is out front, but this one was not given in standard form. The highest power I see is a 12th power. That has 12 zeros. And you might be thinking to yourself, I hope you're thinking to yourself that, well, holy cow, Mr. Hartz, 12 solutions, that graph must be bending all over the place. How can it cross the x-axis 12 times when it's only got 3 terms? And that's a very interesting point that we'll talk about here in a little bit. All right, example 2, here, again, just kind of broadening our look at polynomial functions. Now we're going to look at how we can use the degree of the function and its graph to help specify what those solutions look like. Because like we said earlier, sometimes they're real, sometimes they're imaginary, sometimes they're coming in conjugate pairs. How can we tell? So looking at this first graph, we've got a degree 4 polynomial. And I notice that it crosses the very real x-axis in 2 places. So it has 2 real zeros, but it was degree 4, meaning that it was supposed to have 4 zeros. That means that the other 2 had to be imaginary. So the real zeros we can find via where the graph crosses the x-axis. But the imaginary zeros, we have to say, okay, how many more zeros should there be based on the degree? For our second example, we have a fifth degree polynomial. You can see it crosses our very real x-axis once, so it has one real zero. That means to be a degree 5, it had to have 4 imaginary zeros. The third graph might as well have been right out of chapter 3. We've got a quadratic, a second degree, and you can see it does not cross the x-axis at all, so it has no real solutions, no real zeros. Both of them, because it's degree 2, it had to have 2 zeros somewhere. Both of them just happen to be imaginary in this case. And lastly, we've got a third degree polynomial. You can see we've got 1, 2, 3 places that graph crosses our x-axis. That means it has 3 real zeros. And since it was degree 3, that's all the zeros it can have. It can't have more than 3, so there are no imaginary zeros. For that function. All right, and this is just a wonderful theorem. I love teaching this one because everything just starts to connect. It's this wonderful pattern that we see. And as we go through and solve, this is a great thing to have at our disposal to know how many answers we're supposed to find before we start working just by looking at the degree of the function. That's incredibly powerful. So hopefully this is something that we really find some value in. It's quick and it tells us an awful lot. All right, now I had mentioned a little cryptically at the start that oh wow, we have a 12th degree. That doesn't seem right. We only have 3 terms in our polynomial. How can that be happening? Well, it is possible for a 0 to be repeated. All right, so if a solution appears more than once, if we were to factor the whole thing out and we see the same factors making the same solutions over and over again, those count over and over again. So this completes our fundamental theorem. And so if we take a look at this table that gives us some examples of that, you can see first off 2x minus 1, that is a first degree polynomial. The only solution is 1/2. We had one real solution there. Next, x squared minus 2 equals 0. That is a second degree function, so it has 2 solutions. In this case, it's a conjugate pairing. 0 plus root 2 and 0 minus root 2, we had 2 real solutions there. For the next one, x to the third minus 8, a difference of perfect cubes. This had 3 for its degree. We had 1 real solution of 2, and then 2 imaginary solutions, the -1 plus I root 3 and -1 minus I root 3. So again, we got 3 solutions, 1 real, 2 imaginary. And then the final equation, x cubed plus x squared minus x minus 1 equal to 0. That was also a third degree polynomial, but notice the solutions. There was -1, -1 again, and then +1. So even though we had that solution x equals -1, we count it twice because it must have shown up twice in the solving there. It counts 2 times. So we still get 3 solutions for a third degree polynomial. It really brings some closure to that pattern and allows us to use it every time. All right, so how do we visualize these repeated roots? Well, a nice little analogy is something I borrowed from a colleague of mine. He calls it husband, wife, brother-in-law. So we have here pictured in the graph, you can see the functions there. They all have zeros at x equals 2, but what pattern do we see? Well, let's take a look. The first one, y equals x minus 2, and we can think of that to the first power. And so we get the solution x equals 2 one time. So the degree was 1 on that. And so we have a graph that just passes right through. It crosses right through the x-axis. For the next one, we had degree 2. You can see we get that solution, x equals 2. That factor is showing up twice. This was what we had kind of casually mentioned up above the table on the last slide. So when that solution is seen twice, it bounces off the x-axis at x equals 2. Graph comes in and bounces off the x-axis. It still intersects it, but it doesn't cross through to the other side. Next, what happens when I see that solution 3 times? So again, I probably shouldn't be using the word degree here, but when I see that solution 3 times, you can see my graph crosses at x equals 2 again. Although it kind of wiggles a bit, right? And then lastly, if I see that solution 4 times, we again have the graph bouncing off at x equals 2. So can we see the pattern there? It crosses, it bounces, it crosses, it bounces. Each one of those functions gave us one solution, 1, 0, but the multiplicity, the repeated root, shows us different things. Okay? Now for the analogy, husband, wife, brother-in-law. I want you to imagine that the x-axis is the front door to a house. Okay, so I'm just going to emphasize those here. And I want you to imagine that a guy is going over to his buddy's house to watch a football game on a Sunday. So degree 1 means there's one person at home. It's just the buddy. So guy walks up to the front door, knocks on the door, says, "Hey man, can I come in and watch the game?" "Sure, come on in. No one else is home. You just pass right through. Come right in and watch the game." So degree 1 is just the husband at home. Degree 2, same thing. Guy walks up to the front door. "Hey man, want to watch the game?" Looks behind the guy at the front door and sees the guy's wife standing there. And like, "No, you're not going to watch football here today. Sorry." So the guy turns around. "I'll watch the game at home." He just turns around and leaves. So that's husband-wife. Because it's not just the husband at home. Guy can't come right through and watch the game. The wife's there, so he's just, "Oh, I'm going to go watch the game somewhere else." All right? Third situation, guy comes up to the door. "Hey, buddy, want to watch the game?" And looks back and sees the wife kind of standing there being like, "Oh, I really don't want you guys to watch football." But then after a little bit of a pause, she says, "Oh, you can come in. You're my brother. It's the brother-in-law coming to watch the game. So yeah, come on right in. You can watch the game too." So this is husband, wife, and brother-in-law. Sorry, I'm taking the time to write this out. But there's still a crossing there, but there was that moment of hesitation where it's like, "Oh, should I go in or should I not? Am I allowed to?" But then ultimately, yes, you can pass through. It's the brother-in-law. So that's kind of the situation I think is a very good analogy for seeing these repeated roots and how they affect our graphs a little bit. All right, so our next example, we have a fully factored polynomial. So it's all factored out for us. That tough work from section 4.4 has been done. And we just need to find the zeros and determine which ones are touch points, which ones are cross points. When does the guy get to watch the game? When does he have to go somewhere else? So I'm looking for all the x's that I see. And since it's fully factored, finding those zeros isn't going to be too difficult, right? So the first one, I've got a loose x. That means x equals 0. And notice that factor is to the first power. It's an odd power. So since that had an odd power, that is a cross point. The second one, x equals 3, is the 0 coming out of that factor. And I see that factor twice, 2 times. Because it is an even power, that is a touch point on the graph. That's the husband-wife case where the graph is just going to bounce off at x equals 3. And then lastly, I get x equals -4 from that final factor. I only see that factor one time. It's a first power factor, so that is another cross point. For letter B, n of x equals negative 3x to the third times the quantity 5x minus 2 to the fourth power. We've only got two zeros here. I'm looking for my x terms. First, that loose x, it's not part of a quantity or anything. That just means x equals 0 is that solution. Notice that loose x is raised to 3, an odd power. Odd powers mean cross points. And the second factor is a quantity, 5x minus 2. The solution coming out of that, imagine setting that factor equal to 0. You would add 2 and then divide by 5. Positive 2 over 5. And I see that factor an even number of times, indicating a touch point. All right, so to fully illustrate, whenever we have a factor shown an odd number of times, the graph will cross at that point. Whenever a factor is shown an even number of times, that's where we have our touch points. Okay, but you can see this builds off our idea of factoring really nicely. Now, example 4, I love this type of problem because this you really have to start putting everything together on your own. So find all the zeros and sketch, it's just a sketch, a graph of the function given in factored form using touch points, cross points, and end behavior. So for letter A here, notice my x's are in factors of x minus 3 and x plus 1, so I get those zeros. At x equals 3, because it was a second power factor, it's a repeated root, that is a touch point. And at x equals negative 1, the factor that came out of was a first power factor. We've got a cross point there. Now, end behavior. I want to imagine, I don't want to go through all the work of foiling everything out, so I just want to look at all the x's and their powers and multiply those together. So my leading term would have this 2 out front. It would have an x to the second and an x to the first. Now again, we're kind of abusing the laws of exponents a little bit because we're just looking at what the leading terms would be. Highest power on x, what's that term going to be? So it's 2x to the third. In this case, if I were to FOIL everything out, I would have a 2x to the third leading this whole thing off. It's a positive x to an odd power, positive leading coefficient with an odd power, or an odd degree, I guess I should say, because I know it's the highest power. That tells me that it falls to the left and it rises to the right. Okay, and that's just going to help me build my graph. I need to know what happens on the ends to make this sketch. All right, so I'm going to go ahead and chart out at negative 1. I know I've got a 0 there, and at positive 3, I know I've got a 0 there, and I know it has to fall on the left side and rise on the right side. I just need to make sure that the graph crosses those zeros appropriately. So I'm just going to bring it through from left to right. I encounter that negative 1 first, and that's a cross point, so I'm going to make sure my graph comes in and crosses cleanly there. No wiggle, no hesitation or anything there. Then it bends around to this next 0, but that was a touch point at 3 before it rises off. And that, again, it's just a very rough sketch, but think of what we're doing here. We're looking at a really complicated function, and we know what's going to happen along the x-axis with that. That's really cool. Let's try letter B. At x equals 0, I do see a loose x, so x equals 0 is a solution. It's got an even power on it, so I know that is a touch point. I got x equals 2 coming out of this factor, which is only seen once. It's a first power factor. That's a cross point. And then I've got x equals negative 3, and I see that is to the 5th power, so that's going to be a cross point. But I know it's got that higher power, higher odd power, so there's going to be that little moment of hesitation. Right? It only crosses through without a hitch when it's a first power factor. For my rules of end behavior, I've got a -4, and then x to the 4th times x to the 1st times x to the 5th. For my end behavior, I'm going to treat this like it's a -4 x to the 10th. A negative leading coefficient with an even power, even degree, is going to fall left and right. And that's all the information I need. Ultimately, when I look at this thing all multiplied together, what are the ends going to do? So let's see, at x equals 0, -3, +2, and I know the ends are both going to fall. Let's follow that through and see what happens. At x equals -3, we had a cross point, but it was one of those moment of hesitation things. So I'm going to make sure my graph has a little wiggle in it as it passes through that. At x equals 0, we had a touch point. So it's going to bend back around and just touch the x-axis there. And then at x equals 0, or sorry, at x equals 2, I've got a cross point. That was just a first power crossing. It's going to sail right through. But again, one thing we should be trying to do, we're learning so many patterns about polynomials and how they behave here and how to connect the factors and the zeros and the degree and all this vocabulary coming together. It's showing us an awful lot. I hope we can take a step back and appreciate all we're able to do just by reading a function and doing some quick little observations. All right, and our final example is to find all zeros using factoring techniques. Now this is something we saw in section 4.4 at the end of the last chapter, or I guess we called it chapter 4a, but now we're going to actually solve. We're going to find the zeros. We're not stopping at the factoring step anymore. So for letter A, I've got a difference of perfect cubes. I've got x to the 3rd minus 5 to the 3rd. So thankfully we've got a rule for that, right? We take that expression without the third powers times, now I'm looking here for first thing, second thing. First thing is x, second thing is 5. First thing squared, the opposite sign from that factor out front. First times second, that's 5 times x, and that's always plus second thing squared. And if you ever wanted to check, just try foiling it back together and see if you get all those cancellations to happen in the middle. Well, this first factor is very easy to find the solution, right? X equals 5. But that second factor will always produce imaginary solutions. So for the second part, we're going to have to rely on quadratic formula. And it's kind of nice to know that we shouldn't be beating our head against the wall trying to find magic numbers or factor it further. It just won't happen. So it's nice to know that we just go right into quadratic formula. Opposite of b plus or minus the square root, b squared, minus 4 times 1 times 25, all over 2 times 1. And again, we covered this in detail in chapter 3, so I hope you don't mind me kind of going through quadratic formula kind of quickly here. Oops, sorry, that was a -75. We would use a factor tree to simplify. And you can see there we got 1, 2 solutions there, the conjugate pairs because of that plus or minus, and then our third solution is the real solution out front. So 3 solutions for a third degree polynomial. The fundamental theorem holds. And what a nice way to check at the end of a problem. Did I get all the answers I was supposed to get? Well, now we can quickly check. Just look back at the degree. For letter B, here we've got a 5th degree polynomial. I'm expecting to find 5 solutions here, either real or imaginary. So let's see. First, I want to look for a GCF. I can take an x out of all those. So x times 3x to the 4th minus 7x to the 2nd minus 10. This x out front, I don't want to lose that. That is one of the factors that will produce one of the 5 solutions we get as we go through and solve this problem. And then this part, man, that looks like a quadratic. It's just all the powers have been scaled up by 2. Instead of a second power leading off, I've got 2 times that. Instead of an x to the first in the middle, I've got 2 times that. So I can still do some of the magic numbers factoring techniques if need be. And let's go ahead and try that. 3 times negative 10 is negative 30. Magic numbers would be a negative 10 and a positive 3. And again, we spent a lot of time in Chapter 3 covering this, so I hope you don't mind for the sake of this video. We'll kind of breeze through that factoring. 3x and positive 1. X, and it looks like that'll be negative 10. Yep, it checks out. The only thing is, though, take a look. If I'm just looking at these 2 factors, if I did first times first, 3x times x, that wouldn't make 3x to the 4th. I have to make these x squared terms in order to have that FOIL back properly. It's called quadratic form, and we saw it a little bit earlier on. I think it was section 4.4 that we talked about this. So what do I have for solutions? I've got a loose x, so x equals 0 is one of my solutions. And then right here, if I were to imagine that factor set equal to 0, I would add 10 to both sides, divide by 3, and then square root. All right, and that's a sufficient answer for now. We would hope that coming out of geometry, you would call this square root of 30 over positive 3. But notice, we got irrational solutions that came in conjugate pairs. So we got 1, 2, 3 solutions so far. Now let's look at that remaining factor. So here, if x squared plus 1 were set equal to 0, I would subtract 1 from both sides, and then square root both sides. Oh, and square rooting a negative, in this case negative 1, that's pretty nice. That's just I. But it is plus or minus because we use the square root property. So we get 2 more solutions there because of the plus or minus. We got 5 total solutions for a 5th degree polynomial. All right, so we really didn't try to bog you down with too much step-by-step algebra that you hadn't seen already. The idea is finding the patterns and seeing why this fundamental theorem works for any polynomial. And that's something that I think, again, is a really big thing to take away from an algebra class in high school. It just starts to stitch back together all these little rules that you've learned along the way. So I hope you've enjoyed this lesson, and I look forward to seeing you again.